Thank you, Patrick. Thanks to the organizers for inviting me here. I just decided last Friday that I was going to come, and I'm glad I did. But before I start on today's talk, let me just embarrass a few people. This is the work that I have with Chris Hiller, and he's right there. And maybe Chris, you can raise your hand. And also, as far as I know, Jia Yi over there, she's you guys have a group looking at singular learning right now. So I won't be at this program, but I hope that if you are interested in singular learning theory, you can look for the two of them and find out more. Okay, now I'll talk about myself. I'm Shaowei. I'm the director of research at the Topos Institute. We are a nonprofit that looks at applied category theory and how it can be used to build safer social technical systems. So today I'm not going to talk about I will talk about categories a little bit, but I want to focus on singular learning. So some of the material here is meant to be like an overview. It's meant to be confusing. And then there will be resources at the end to kind of guide you if you're interested in learning more. So let's jump right in. So I want to first start with defining relative information. So I have to tell you that I have this obsessive fascination with KL divergence or relative information. It is like the number one thing that I look at all through my life, and I'm just adore this thing so much. And I hope I can pass on some of that enthusiasm to the rest of you today. So to me, all right, so what is relative information or the KL divergence? So suppose you have probability distributions P and Q on a finite set, then the KL divergence or relative information from P to Q is defined as the sum of Q log Q over P. And more, if you are working with continuous random variables, and you have densities P and Q, then the relative information is given by this integral, the integral of Q log Q over P. Now, when we write down these integrals, we often assume that that when P goes 0, Q will also be 0. And so this means that Q is P is absolutely continuous with respect to Q, Q is absolutely continuous with respect to P, or P dominates Q. More generally, if Q and P are measures with the same total measure, and if the total measure is not equal to 1, if, again, P dominates Q, then you can define this random Nicodim derivative. And then in that case, we will define the relative information to be the integral of log of the Rn derivative with respect to dq. And this is well defined. In fact, we'll see that this more general form of relative information has many of the nice, wonderful properties that we care about in statistics. Now, when you see the word Q in my talk, you should think of Q as a reference or a true distribution. Or, if you're talking about, I really like Dan's talk this morning, Q could be a teacher network, for instance. And we often want to understand the distance of a model distribution or student distribution P to this true distribution Q. And just be aware that this distance is, I mean distance in quotes, it's not a symmetric distance. So the distance from P to Q is different from the distance from Q to P. Now I'm going to rant a little bit. Right, relative information as a concept is very well defined for a large class of statistical models. A lot of approaches in information theory tend to focus on entropy. Entropy, on the other hand, is often ill-defined, except in certain special cases like in finite sets or certain kinds of continuous sets. But in all of those cases, you can redefine entropy as a special case of relative entropy. More precisely, if you are trying to find the entropy of some distribution R, then what you can try to do is create two distributions. So the first distribution is called the copy. So you take a joint distribution on two variables, x and y, where you have R on x and R on y, and then they're completely independent. Or you can have what we call the diagonal distribution, where the probability of x and x is equal to R of x, but then if x and y are different, then the probability of joint distribution of x and y is 0. Then if you find the KL divergence from the copy to the diagonal, you get at precisely the classical entropy. So to me, I prefer to think of relative entropy as being more fundamental than entropy itself. And to remind me that information in a distribution should always be measured relative to another distribution, Q, I always have this mantra in my head that information is relative. Okay, when you're talking about information, you should always ask yourself what you're comparing your model or your distribution to. So let's jump right into the meat of singular learning. Okay, so this is I'm going to talk about the convergence of stochastic complexity, one of the key results in Watanabe's textbook on singular learning. So we start with a parametric model, P x of omega, and suppose we have a prior phi, and suppose that Q is our true distribution, and then suppose we observe n samples of data from that distribution, independent IID, and then so we can ask what is the marginal likelihood of that data. So the marginal likelihood is the integral of the product of the probabilities of the data points with respect to the prior. Now we can also define the entropy. The empirical entropy of the data is going to be the sum of the log of the Q of the distribution Q on the axis, averaged by the number of data points. And then lastly, we have the we have the relative information I of W, which is the distance from the model P of X given W to Q. So now we can state Watanabe's theorem. Watanabe's theorem says that stochastic complexity, which is defined to be the negative log of the marginal likelihood, okay, it has an asymptotic expansion as the number of samples go to infinity, and that's going to be n times the empirical entropy. So that's it's a standard term. We expect this integral to behave mostly like n log n times the entropy, but you also have a log n term, and the coefficient of that is going to be called lambda. You also will have a log n term, where the coefficient is going to be theta minus 1. I'm going to tell you what lambda and theta is in a moment. And then lastly, you have some noisy term, because remember Zn here is a random variable. It depends on the data, right? So this is a random variable, and all the randomness is now taken away, squeezed into this small little variable here, which converges in law to a constant. And so what is this magical number lambda, and what is this magical number theta? It is called the real log canonical threshold, which I'll define in the next slide, of the KL divergence over our parameter space omega with respect to the prior phi. And theta is the multiplicity of this real log canonical threshold. And from now on, I'm going to say RLCT instead of a mouthful of words. And in the special case when we have regular models, in statistics, a regular model is one where the Fisher information matrix is non-degenerate. In the regular case, then this theorem simplifies to the Bayesian information criterion, the BIC. Okay, so this is a vast generalization of the BIC. And the proof of this took pretty much half of Watanabe's textbook. It's very involved, a lot of deep statistics in there, and algebraic geometry and other things. Quite an incredible feat. But yeah, it's amazing that after all that, you could basically simplify the asymptotics of stochastic complexity to this. Okay, so what is this magical number, the RLCT? So suppose you gave me a function f that is I should mention that is a non-negative function where f at the origin is 0. And so if I were to plot, say this function, say f is a function in two-dimensional space, then I can plot this out and it could look possibly something like this. You can think of it as a distance, some kind of a distance function. What we care about is to look at the volume of the tubular neighborhood of f. So you look at f less than some epsilon, okay? It defines some neighborhood, and you ask what is the volume of that neighborhood? And you want to ask what happens when epsilon goes to 0? What are the asymptotics of this volume? Okay, so for instance, if f is just, say, like the squared Euclidean distance, then the volume of the tubular neighborhood would basically be a volume of the n sphere. Okay, you can show that at least when f is algebraic, is a polynomial, that this tubular volume has asymptotics that look like this. It's some constant c times epsilon to the lambda and minus log epsilon to the theta minus 1. And here lambda is going to be our RLCT, is defined to be the RLCT of f, and theta is going to be a multiplicity of that. And you can prove that theta is going to be a positive integer and that lambda is a rational number. And so lambda is not just a real number, but lambda is actually a rational number. So this proof is done using some advanced Russian mathematics from the 1960s and some beautiful piece of math as well. So as I said, when f is the squared distance to some smooth manifold of codimension d, then lambda is going to be d over 2, and theta is going to be 1. Multiplicity is just 1. Okay, so with Watanabe's theorem, we now know that if we want to find the asymptotics of stochastic complexity, you should look at the RLCT of the relative information. But most of the time, relative information is this ugly function that has logarithms, integrals, and a lot of other nasty things in it. It's usually not a polynomial. It's usually also not analytic. I can point you to some papers about that if you're interested. So how do we compute the RLCT of a nasty function? It turns out that in many statistical cases that we care about, it reduces to computing the RLCT of an ideal. So here, when I say ideal, I mean it in the sense of algebraic geometry. An ideal is a set of polynomials which are closed under linear combinations and products by other polynomials. So let me just now try to define what is the RLCT of an ideal. So just now we talked about RLCT of a function. Now I'm going to tell you the RLCT of an ideal. So suppose I have two sets of polynomials, f1 to fm and g1 to gn, and suppose they generate the same ideal. They generate the same set of polynomials, j, and we also assume that all of these polynomials, they vanish at the origin, right? Then the RLCT and the multiplicities of the sums of squares. So you construct f to be the sum of squares of f1 to fm, and then you construct g to be the sums of squares of all the g1 to gn's. Then the RLCTs of these two functions, f and g, are actually identical. Okay, so and the multiplicity will be the same. And because they're identical, it doesn't matter which set of generators we're picking. We can just define the RLCT of the ideal to be the RLCT of the sum of squares of its generators. So this goes to show that this RLCT has some wonderful algebraic geometric properties. Is an algebraic geometric invariant in a sense that it does not depend on how you parameterize the model or how you parameterize your functions, or how you pick generators for your variety, if you understand what a variety is, and it's going to give you the same number.
Question?
Yes.
When you replace one of the set of polynomials by, say, the Grobnier basis for the first,
yes,
does this square has any algebraic interpretation? I mean, if you replace like one to be minimal in some sense, for example, Grobnier basis for whatever.
Mm-hmm. So yeah, you could, if I understand your question right, you could replace the f's with a Grobnier basis for your ideal, and it would work.
Yeah, but then that quantity, does it have any particular meaning?
The sum of squares of the Grobnier basis? Not really. To some extent, if you look at f of 0, f equals to 0, then it cuts out the set theoretically. It cuts out your variety of your ideal. Okay, but then ideal theoretically, what's good? Yeah, f may some. Yeah, I won't talk too much about that, but yeah. So f of 0 gives you your variety, because f is 0 if and only if each of the terms here in the sum of squares is 0. Hope that's okay. So so I was saying that in many statistical settings, for instance, for discrete random variables, it helps to not have to think about this ugly ugly relative information. Instead, we could look at, suppose we have a discrete random variable and that we have a parametric model for the k states of this discrete variable. Then it's enough to look at, and suppose our Q distribution is P of 0, assuming that the parameters have been shifted to the origin so that the origin corresponds to the true distribution and the true distribution lies in your model. Then the RLCT of the ideal, which is given by the difference between the PIs and the QIs, that will give you the RLCT of your stochastic complexity. Okay? And so these turns out, in a case where your PIs are all polynomials, this will give you a nice polynomial ideal. And so you get this very combinatorial problem of trying to compute RLCT of a polynomial ideal. In a case where we have Gaussian random variables, it's the same thing. Suppose for the simple case, we look at the case when the mean is 0 and we are only parameterizing the covariance matrix, then the real log canonical threshold of the relative information is given by the real log canonical threshold of the ideal generated by the sigmas, the entry sigma ij's minus the true values. Okay, so there are computational tools. We have computational tools now to compute the RLCT of simple statistical models. And there is a relationship between RLCT and tropical geometry, if you guys are very interested in tropical geometry. So for instance, computing, for instance, the RLCT of an ideal sometimes requires quite a bit of work, like trying to resolve the singularities of an ideal. And if you're in a rush for time and you only have like 10 minutes before you have to do a presentation to everyone about singular learning theory, then what you could do is you could take the ideal and you generate the Newton polyhedra. And this is how you do that. You take each polynomial that you have in your ideal, you look at each monomial of that polynomial, and for each monomial, you take the exponent, alpha, and you consider the orthon whose corner is at alpha. So it looks a lot like one of these blue regions, squarish regions that we have here. And what you do then is that you take the union of all these orthons, you take the convex hull, you're going to get a polyhedra, which could be infinite in size. And then that's called the Newton polyhedra of J, the ideal J. Then if you want to estimate your real log canonical threshold, what you do is, first you have to pick a direction tau, all right? In this case, our direction tau is going to be the 1, 1 vector, the all ones vector, okay? And then you ask, when does this line that starts from the origin and goes in the tau direction, when does it intersect my Newton polyhedra? And the moment that it intersects the scaling constant t that you multiply to your tau to get the intersection point, that's going to be called the tau distance. And then the multiplicity of the tau distance is going to be given by the codimension of the face of the Newton polyhedra at this intersection point. Okay, so if we look at this, it's kind of small, but you can see that the distance is 8/5. And because this face is codimension 1 in 2-dimension space, so the multiplicity is given by 1. And there's a theorem which says that the real log canonical threshold of J is bounded above by the 1, 1 distance and the multiplicity. And we get exact inequality when J is a monomial ideal. In other words, J is generated by monomials. So there's a very interesting connection between RLCTs and tropical geometry, which looks at Newton polyhedra and combinatorial objects of that kind. And therefore, there's a connection between tropical geometry and statistics, right? Because statistics tells us that that stochastic complexity depends on the RLCT, and then the math tells us that RLCT depends on the tropical geometry of our model. So now what other magical things can we do with singular learning theory? So what I've done so far is talk about some of the math, the computational tools for that. Now I'll jump a little bit more to applications. So suppose we are working with Bayesian inference. And let's say we have a belief that's given by our prior P on the parameter space, and then we have n sample points. So in Bayesian inference, we update our prior belief to a posterior using this rule here. And then we then infer the probability on new data points using the predictive distribution. So predictive distribution is going to be the integral of the model P of x given omega w multiplied by the posterior. Okay, so that gives you the predictive distribution. So this is a very simple approach to taking a parametric model and then trying to predict probabilities on new unseen data. Now the question is, what is the generalization error of such a learning algorithm? Okay, so the generalization error of Bayesian inference is defined to be the relative information from the predictive distribution to the true distribution. So, it's in the case of finite sets, it's just given by this. And now let lambda be the RLCT of the KL divergence between the true distribution and the model. Okay, so I want you to see the difference between these two here. This Gn over here, it is a random variable because P star of x, the predictive distribution depends on my data. Here, this K of W, it is a function on W. It's not a random variable. It is the distance from the true distribution to a point in my model. Okay, and the deep theorem of Watanabe says that the expectation of the generalization error is asymptotically lambda over n, where lambda is your RLCT. So you can see that this is actually quite related to Dan's talk this morning, where we are also seeing some kind of complexity over n for the risk that he was looking at. And here, this generalization error is a measure of the risk, and the expected value of this risk is given asymptotically by lambda over n. So if you want to know the generalization error of just good old-fashioned Bayesian inference, you have to find the RLCT. It is a fundamental thing in statistical learning.
Excuse me, what's the constant in the big O?
The constant here?
Yes.
Oh, sorry. In this case, there is no constant.
Okay,
There's no constant because it's already, entropy has been subtracted out here. Q log Q is your entropy.
I mean, you write big O of 1 over n. What's the constant?
This is O of n, so something smaller than 1 over n. Something that asymptotically is smaller than 1 over n.
Little o.
Little o. Oh, little o, yeah. I'm sorry about that, yeah.
Okay.
Something smaller than 1 over. Thanks for the question. Okay, so let's look at another possible use of singular learning theory. This is something that a few others are people, Dan Murphat, Jesse Hoagland, Alexander Odenziel, and others from Timaeus, they have been working on. So we look at, okay, we're thinking about, in classical statistical learning, maximum likelihood is a very popular method for training your model, right? You start off with your data, you write down the likelihood of the data, and then you compute the maximum likelihood estimate, okay? And you often do that by computing doing gradient descent on this likelihood function. And we mostly know that the problem is that when you do maximum likelihood estimation, you tend to overfit the data, and perhaps we have been doing it all wrong. What if we decided that instead of using likelihood as your function that you are trying to minimize, we should just minimize relative information? Now, maybe you could argue that, hey, you can't use relative information as an objective function because we don't know what the true distribution is. Because if you knew what Q is, then you don't have to do machine learning. But I would say that despite not knowing Q, let's just try to push ahead and see what we can do if this was indeed our objective function. You take the derivative of the relative information. This gives you this sum over the gradient of the log likelihood with respect to Q. Now, if you wanted to estimate this gradient, one way to estimate it is just to sample x from Q and then just take a 1-point sample of the gradient. And it turns out that this gradient step here is precisely the same as the gradient steps that we took in maximum likelihood estimation. But this time around, because we're sampling, we don't have deterministic gradients, we actually have stochastic gradients. And so if you're doing stochastic gradient descent, it is almost as if you are using the KL divergence or the relative information as an objective function, right? Now, if that's the case, then we can start to think about things like, why is it that if you use stochastic gradients, you don't tend to overfit so much? Why is it that we have something called double descent happening when we do stochastic gradients? Is there a way to think about the asymptotic behavior of stochastic gradient descent from the point of view of singular learning? This is exactly what a bunch of people have been thinking about and are thinking about right now. There are so many other cool things about singular learning that I won't have time to present, but in singular learning theory, at the heart of it, we look at three different kinds of mathematical constructions. The first is what we call the state density function. Here, if you integrate the state density function, you will get the tubular volumes that you saw earlier. All right, here delta is your direct delta. Now, if you took the Laplace transform of the state density function, you're going to get the partition function, okay, which is the marginal likelihood. And if you took the Mellin transform of the state density function, you get something called the zeta function, which is not unlike the zeta function that you see in number theory or in the Riemann hypothesis. So it turns out that in order to get many of the results that Watanabe had in his book, he actually had to understand the zeta function of the statistical model and then go through this way to get some results on how the partition function behaves asymptotically. Okay, for those who work in quantum physics, this should not be a surprise. There's a lot of work with zeta functions and partition functions in quantum physics, but this is the equivalent for statistical learning. Okay, more resources. There are two books that a lot of people read. This is called the Gray Book and Watanabe's Gray Book, and this is called Watanabe's Green Book. Okay, he has a website where you can find out more about SLT. I have some resources on SLT on my website. You can also go to a website called singularlearningtheory.com, or you can go to Timaeus, which is a nonprofit that is looking at using SLT to understand neural networks. So there's a lot of interesting work. Any questions at this point? Yes?
The Bayesian information criterion result, if I understand correctly, it's assuming a parametric model. Are there analogs of these outside parametric setting?
Yeah, that's a very good question. I think Watanabe I have not done work outside of the parametric setting. Watanabe, I think, has written quite a few papers about neural networks, looking at cases where, looking at ReLU networks, looking at cases where your true distribution is not in the model, and things like that. But so that's all I can say. I don't know more about that. Yeah, but that's a very good question. Okay. So I'm going to take a slight turn in direction and now talk more about relative information. So since working on SLT, which I did for my PhD thesis, I've become more interested in understanding why relative information is so relevant. I've been thinking about it more from the point of view of category theory, understanding the structure of relative information, how it for instance, works really well with compositions of functions, compositional models, and things like that. So I'm going to share a little bit about that today. So first, I want to define a slight generalization of relative information called the conditional relative information. Okay, so if you have random variables x and y, then the relative information from P to Q of x condition on, of y condition on x is going to be the relative information of Q of y given x from P of y given x. So you're just looking purely at the conditional, the KL divergence between these two conditional distributions, and then we average it out with Q of x. So in the sum, x is fixed, and then you average it out with the true distribution on x, q of x. And that's going to be the conditional relative information. Okay, so this conditional relative information is used a lot in variational inference, EM algorithms, free energy, active inference, and things like that. Now, as I said, I like to go beyond statistical distribution. I want to look at measures. If x and y are, p and q are not distributions, but they are just general measures, then we can define a conditional measure given by the same formula that we had for statistical distributions. And in the same way, you can define conditional relative information for measures. Okay? And if you want to get back to statistical relative information, then what you do is you just take your relative information for measures and divide it by the total measure on Q, and then you get your good old-fashioned statistical version. So I think one of the most beautiful things about relative information is that it satisfies something called the chain rule. So if you look at if Q and P are joint distribution on X and Y, then the relative information from P to Q for X and Y, it breaks up into a sum. It breaks up into the relative information on X plus the relative information of Y given X. And if you care about category theory, the way you should think about this is that you have your terminal object giving you a distribution on X, which then you care about the distribution, which then from X you have a conditional map to distributions on X X and Y, observation X and Y. And so here you have your relative information on X, and here you have your relative information on Y given X, or another way to say this is actually Y and X on X. And then it turns out that the relative information on this entire chain is just the sum of the top two. So relative information respects composition.
What is the first thing? Is there a one point set?
Oh, so this is a terminal object. So it's just a 1 point. You can think of it as a 1 point set, and then the conditional map from a 1 point set into this. Sorry. Yeah, I'll discuss this a little bit more later. There will be more details about this. Yeah. Okay. So besides the chain rule, we also have sums and products. So for instance, if I take two measures, one P and Q, one on X and one on Y, what I can do is look at the disjoint union of the sets X and Y and consider the measure given by P, which I call P plus Q, which is the measure P on X if X is in X, if this input thing is in X, and if the input here is Y, then the measure is given by Q of Y. All right, so we can have basically you have the disjoint union of two measures. You can do that in this category. You can also take the Cartesian product of measures. So if P and Q are two measures, you can take their Cartesian product where the measure on X and Y is going to be P of X times Q of Y. Then we also know that the total measures of this disjoint union is going to be the total measures of P plus the total measure of Q, and the total measure of P times Q is going to be the product of their total measures. Okay. So that was for total measure, and it turns out for relative information, you have the same structure. All right. If you have sums and products, then the relative information from P1 plus P2 to Q1 plus Q2 is going to be the relative information from P1 to Q1 plus the relative information from P2 to Q2. So relative information respects disjoint union. Okay, and then same thing with products. If you have P1 P2 as a product and Q1, Q2 as a product, then the relative information has a much more complicated formula, but it turns out there's a good reason for this, okay? It turns out that you first take the relative information from P1 to Q1, and then you multiply by the total measure of Q2, plus that from P2 to Q2 multiplied by total measure on Q1. There has been an observation about a decade ago that this looks a lot like the product rule for differentiation. All right, in differentiation, the derivative of over the x of f and g is f dg dx plus g df dx. Okay, and so this looks a lot like that, and in fact, there's a very good reason for this.
I mean, differentiation when there is no curvature, I guess.
No, yeah, you have to. It's not differentiation in the sense of curvature, but it's like yeah, but it has the same form. It has the same form. It has the same form as differentiation. Okay, so there have been a lot of work by others about looking at the chain rules, sum rules, and product rules, and asking if they completely characterize or axiomatize relative information. There are some of the papers that look into that are here. I'm not going to talk about that today, but it's also an interesting topic for people looking at relative information. Okay, so up to this point, I've given you very tantalizing properties of relative information. The chain rule, the sum rule, and product rule, they're meant to conjure up in your head thoughts about calculus, right? Like in calculus, we also have the chain rule and sum rule and product rule. So how is relative information maybe related to calculus or differentiation? So to do that, we have to introduce the dual numbers, right? So a dual number is a semi-ring or a rig where you first take all the positive reals, non-negative reals, you append an arbitrary variable epsilon to it, and then you take the quotient over the ideal generated by epsilon squared. Okay, so if you don't like this algebraic geometric description of the dual reals, another way to think about it is that you take the non-negative reals and you append a new variable epsilon that you can think of as an infinitesimal, such that if you have epsilon squared, it becomes 0. Okay, so all the elements of this is going to look like a plus b epsilon, and then you can add them to each other. So you just add them element-wise, a plus a prime or b plus b prime, if you have two different duals and adding together, and multiplication x by expanding out this sum and then taking all the epsilon squares to 0, right? And now, what I'm going to do is to take this semi-ring and to convince you that it is a category. Okay, in category theory, we have objects and we have morphisms. For those who are not interested in category theory, you can just switch off for a moment. But you want to think about a number a plus b. Okay, so when we have the dual real number a plus b epsilon, we think of it as a loop that's on the object A. So we have objects A and maybe A prime, and then we are going to have loops on each of those objects, many different kinds of loops, and each of those loops is going to stand in for a dual number. And when you compose two loops or two of these morphisms together, they compose by addition. They compose by multiplication. They compose by multiplication. And then we have the identity morphism, which is given by a plus 0 epsilon. This is going to be your identity morphism. Okay?
Can I ask a question?
Yes.
What is the square root of epsilon?
Square root of epsilon?
Are you allowed to talk about the square root of epsilon?
No, we don't have square roots. Epsilon does not have square roots in this system. Yeah. Thanks. Okay, so we have this category here, and then it also has it also has sums and products in this category, okay, just like the what we saw previously, and so this kind of category is called a rig category. So it is a category that has additional structure. It has sums and products in this category.
Can I ask a basic question?
Yes.
Sorry. I have maybe like a very computer science-centric view of category theory. And so I usually think about understood morphisms as maps, but you're saying like the morphism A plus C, B plus D, epsilon. Where's the map? What's the map? You know what I mean?
Yeah, so in category theory, morphisms can be thought of as maps, but there are also there are categories out there where the morphisms don't correspond to any kind of meaningful map.
Okay.
So I think
I should shed that idea.
You could shed that idea, or you could say that, yeah. So precisely when the times when you can think of morphisms as maps is when you take this category that you care about, and then you ask if there's a functor to the category of sets. And if there's a functor to the category of sets, then your objects are going to map to sets, and then your morphisms are going to map to maps. But if there isn't such a functor, then I think in the case of this, there is such a functor, but the one way to think about this is that each of this is a point on the real line. The loops are the tangent spaces, they form the tangent spaces, and the maps are going to be given by translation in that tangent space. So I think here you can think of it as a map, as you said. Yeah. So I'm running out of time. I'm trying to think about how to do this. I think what I'm going to do is I'm going to somewhat jump to the punchline, and then talk about why I think this is very important for machine learning, statistics, and understanding of AI. Okay, so we have this rig structure on the dual numbers. And just now, when I talked about relative information, I alluded to some kind of rig structure on random variables and conditional maps between random variables. Okay, I won't go into detail about what that rig structure is, but if you kind of follow what I said earlier about relative information, then you can see, okay, I see products and sums happening with random variables. I can believe that. So there is a rig structure there. Okay, and now, I'm going to skip this part. And so, given that there is a rig structure on our random variables, okay, and that the category of random variables with their conditional maps with their rig structure, I'm going to call that P, and the category of the dual numbers, I'm going to call that R, and I'm now going to construct a very special functor between these two categories. In this functor, I'm going to take every map, every conditional map from some random variable y to random variable x in P. I'm going to map that to the dual number where the A, or the first number, is given by the total measure, and the second number is going to be given by relative information times epsilon. Okay, it's a very strange map. I'm going to map, in fact, this is called a functor. Okay, a functor is a map between categories that has a lot of nice symmetrical properties. But I'm going to map each conditional map into this dual number. And it turns out, if I do it this way, then this functor, this map that I constructed is not just any ordinary map. It is actually a rig monoidal functor. In other words, it preserves the structures that in P and maps it into equivalent structures in R. Okay? So in other words, if you are trying to take your category of random variables and their conditional maps, and you're trying to make sense about that, and then you try to take that information and you try to feed it into a computer and you try to reduce it to a bunch of numbers and you hope that you can do machine learning on it, it turns out the one beautiful way of taking all this structure that you have in your random variables and trying to map that into real numbers, hoping that the structures get preserved, it turns out the only way to do it is to do it with the total measure and relative information. Okay. Yes, Dan.
So can you give a like intuitive explanation for why epsilon squared equals 0 is a is the right thing?
Yeah, that's a very good question. So, first of all, as I said, relative information has a product rule that looks a lot like the product rule for differentiation. So it tells us that, to some extent, relative information is doing calculus in some other kinds of space of some other tangent space. And it turns out the tangent space that I'm trying to talk about is this tangent space here. So which is why if you're talking about one-dimensional tangent spaces, then you ignore epsilon squared. You ignore the higher order terms. We're only doing the first order calculus, then relative information only respects the first order terms, and so the epsilon squared terms disappear. The next question is to ask if suppose we want to look at, instead of the dual number, suppose we wanted to look at something with more structure, where the epsilon cubes disappear, but epsilon squared does not disappear. And then if we try to construct a functor from P into this higher order tangent bundle, what do we get? Well, the first few terms are going to be the same, your total measure, your relative information. The question is, what is the second order term here? And the answer is some kind of higher order mutual information. There's a paper by Vigneaux and Daniel Bennequin and others that have looked at this question. And these higher order mutual information, they're not the first to discover this in their 2015 paper. There was earlier work in the 1980s by a statistician who looked at these higher order mutual informations and said, these are beautiful things, we should study them. But in statistics and machine learning, we haven't actually touched on that very much. I haven't seen a lot of people use these higher order mutual informations. Yeah. And you can look up in my slides, I have a very rough proof outline of why this thing here is a Rig monoidal functor. And then you'll see that I have to use everything I know about chain, sum, and product rules to do this. Okay, so here's the summary. Information is relative. Information is energy. If we are thinking about doing machine learning and statistical learning, it really helps to think about its relationship to statistical physics, where in statistical physics, we are minimizing energy instead of information. And in statistical physics, I don't know if relativity in physics is the same as relativity for information theory, but relativity is important for understanding information theory. Second thing is that there is a lot of beautiful algebra, geometry, and combinatorics, as I showed earlier with Newton polyhedra, that can help us to understand asymptotic behavior of statistical models. The third thing I want to say is that relative information is a very beautiful object. It's somehow the only object that can preserve all the messiness that you have in statistical learning and compress them down into the real numbers or the dual numbers. It is the only thing that can do that. And that's why it's shown up everywhere in machine learning. And lastly, I just want to tease a little bit. There was John Wheeler talked about it from bit, that everything in this universe is just information. I do think that, to some extent, I hope one day we can say with certainty that everything that we see around us, neural networks, physics, it comes down to relative information, it from bit. Yeah, thank you.